In today's video, we're going to talk about the superposition and standing waves. So let's just start by saying that sound is a wave, and a wave is all about motion. So how can it create something that looks perfectly still? How can waves of pure vibration produce regions of absolute and moving silence, while other regions vibrate like crazy? The answer is a phenomenon. Well, the answer is pretty simple, and it's a phenomenon that goes way beyond just adding and subtracting waves. It's not just about what happens when waves meet, but what happens when they get trapped. Last time, we explored the fundamental rule for all waves in the universe, the principle of superposition. We saw how waves can build each other up or cancel each other out into total nothingness. But that was just the beginning. That's what happens when waves are free to pass through each other and go on their way. Today, we're asking a much deeper question. What happens when they cannot escape? What happens when a wave is confined to a space, forced to meet its own reflection over and over again? The result is one of the most foundational ideas in all of physics. It's a secret behind every musical note you've ever heard. It's why your microwave actually works, and it even hints at the foundational nature of reality itself. We're going from traveling waves to standing waves, and you're about to see how simple interference, when trapped, builds something entirely new and surprisingly. So let's start by superposition refresher. Before we trap our waves, let's just recap the principle that makes all of this possible, the principle of superposition. I know it sounds fancy, but it's a beautifully simple idea. It says when two or more waves overlap, the total effect is just the sum of what each wave would have done on its own. And to give you a better visualization, imagine two waves traveling down a rope toward each other. For example, this one is y1 going to the right, y2 going to the left. If a crest of one wave meets a crest from the other, their height would add up. So the new wave would be something like this, y1 plus y2. The rope at that spot shoots up to their combined height for just a moment here. And that's the constructive interference. They build each other up. For example, if this one is A1, the amplitude 1, and this one has an amplitude of 2, the new amplitude A3 equals to amplitude A1 plus amplitude A2. And now imagine the opposite. A crest meets a trough, a valley of another wave. If they have the same size, the upward pull of the crest is perfectly cancelled by the downward pull of the trough. For that one instant, at that one point, the rope is perfectly flat, as if no wave was there at all. So that's the destructive interference. They cancel each other out. To give you a better visualization again, imagine this is our crest and this is our trough. They're moving towards each other, y1, y2. At that very specific moment, when they meet, their effect would be zero amplitude if they would have like same amplitude. A3 equals to the A1 plus A2. However, here the difference is if this is our A1 and this is our A2, A2 is a negative amplitude, is a negative A1. And this rule is absolute bedrock in every complex wave pattern you can think of. From ripples in a pond to the single hitting your phone is just a simple addition and subtraction happening over and over again, just like we saw. But this simple rule leads to some incredible results when we add one more ingredient, a boundary. And so far, we've been imagining our waves traveling freely, just like here, just like the example that we said. But in the real world, waves are always running into things. They hit walls, they reach the end of it. They reach the end of a guitar string, they bounce around inside a flute, they get confined. And when a wave hits a boundary, it reflects. This single act of reflection is what turns simple superposition into something spectacular. And now let's picture this. Imagine you're holding one end of a long rope. Like, let me draw it like this. This is our rope, and this is our wall. That post is a fixed boundary. The boundary is fixed. You send a single pulse, a crest, down the road. It travels along a neat little bump of energy. What do you think happens when it hits the post? You might guess it right. Well, the wave tries to pull the post upward, and I would draw it later. Tries to pull the post upward, but the post is fixed. So thanks to the Newton third law, the post pulls back down on the road with an equal opposite force. This down thought kicks off a new pulse that travels back towards you, but it's not the same pulse, it's inverted. Your upward crest has been reflected as a downward trough. It's been flipped upside down, or as physicists would say, it's undergone a 180-degree phase shift. And this is critical. A wave reflecting from a fixed end always flips. This is what you always need to remember. And you can always drive from the Newton third law, but you can remember it. The thing was, a wave reflecting from a fixed end, let me draw it, fixed end always flips. So let's draw it. This is our pulse, for example, going to the fixed end. And then when it reaches there, at this position, for example, the wall tries to pull wall up, but it can't because it's fixed. So the wall pulls an inverted pulse toward the source of the wave. So the reflected wave would be inverted. It would be like this, going to the left instead of going to the right, for example. And that's our fixed boundary. And now let's say, what if the end isn't fixed? What if your rope is tied to a loose ring that can slide up and down? This is a free boundary. Now, when your crest gets to the end, like just here, the ring is free to move. So the pulse arrives. Paul pulls the ring up, and the ring is just to slide up and then back down. Okay? Kicking off a reflected pulse. This time, because nothing was holding it back, the reflected pulse is not inverted. You send a crest, you get a crest back. So, we got two kinds of reflection, the fixed end and free end. The fixed end, the wave flips upside down, and the wave reflects, for the free end, the wave reflects right upside. So, if we want to draw this again, it would be something like this. For example, this is our light wall, and we put and it's a free end. So, and this is our wave. It goes there. It pulls it up. Let me draw it in the same scale. So it pulls it up, and then our wave would be like this, and then it goes down, so nothing would be inverted here. It just gets to its position in the same. You send a crest, and you would get a crest, and that's what happens in a free end. This might seem like a tiny detail for you, but it changed everything, because now we have the perfect setup. We have the original wave here, for example. We have the original wave you send traveling in one direction, and we also have the reflected wave with the same frequency traveling in the opposite direction, both trapped on the same rope, and according to the superposition, these two waves have to interfere with each other. The pattern that emerged from this constant traveling interference isn't a traveling wave at all. It's a standing wave. So now, let's talk about standing waves in the real world. And this is just, like the thing that we talk about, this isn't just a theory for ropes. The exact same idea applies to sound waves trapped in a column of air, which is how every wind instrument works, from a piccolo to a pipe organ, for example. Sound waves are compression of air, but they still reflect, interfere, and create standing waves. The trick is figuring out the boundaries, what happens at the end of the pipe. Before jumping into the quick concept, we can think about the sound wave in two waves: by the displacement of air molecules, and by or by the pressure, unlike how squished together they are. Think about it. Where the air molecules are sloshing back and forth to the most maximum displacement, the pressure is actually stable and normal. But where the molecules get jammed up and can move at all, when we have zero displacement, they get super compressed and then super stretched, creating a huge pressure swings. So displacement antinode, when we have the maximum movement, is a pressure node. When we have a stable pressure and everything else. So like if we have a displacement node, minimum movement, it's a pressure antinode, the most unstable, the maximum pressure. And so, but to keep the thing simple, we'll talk about displacement, but I would show the graph of pressure to like visualize it better. So we have three cases. Case one is an open tube. Open tube. Case two is open. Let's just start by open closed. Yeah, open closed. And case three is closed. So let's just start by talking about the case one, the open tube. Case one, open tube. Imagine a pipe that's open at both ends. For air, an open end is a free boundary. Molecules can rush in and out easily. Let me draw it first. For the open. This is our column. And then we have, as you can see, air molecules, for air molecules, these places are like free boundary. Molecules can rush in and out easily. This means an open end has to be a point of maximum movement, a displacement antinode. So we have antinode here, displacement. I wrote the displacement here, antinode and antinode. So for an open tube, we need a pattern with an antinode at each end, and the simplest one that fits is an antinode, and then we have node, and then we have antinode, and this is exactly 1/2 of a wavelength fitting inside the tube. So just like our string, the length of the tube L equals to the half of the wavelengths in this case. The next harmonic adds another node, becoming antinode, node, and no antinode, node, antinode, node, antinode. That's one full wavelength inside the tube. And then we're going to draw them now. So we said we have an antinode here, and this is a node. So node is the minimum displacement or zero displacement, but we have an antinode here, so it's a maximum displacement. So if we want to draw it, it would be something like this. And this is our M1, mode 1. In here, the L equals half a lambda. So our lambda would be 2L. And our frequency, it's V over lambda. So it would be V over 2L. Just like same as a string. And we call this first harmonic. Then, again, we said the pattern is we have antinode at both ends. Antinode, antinode. But here we have node, antinode, node. So when we have node, there is a minimum displacement. There's a minimum displacement here. And then our pattern would be something like this. This is our mode 2, and here our L is equal, lambda equals to L. So the frequency equals to the V over L which is again 2F1. It's twice the first harmonic, and we call it second harmonic. We're going for the third one. We have a 2 like this. I would call it A and N to like simplify it. A, we have an antinode at both ends. We have A, since this is mode 3, we would have 3 nodes, just like here when we were in mode 1, we have 1 node, we had 2 nodes here, and now we have 3 nodes. Antinode, node, antinode, antinode, node, antinode, node, and antinode. So our pattern, since ends and nodes have, why did I draw a dot here? Okay, N, N, N. So we have 3 nodes and 4 antinodes. Nodes have the minimum displacement, so there would be no displacement. And then our pattern, our waves would be like this. I'm sorry if it's not on the dot, but that's the best that I can do. So that's how we can draw for mode 3. So lambda, for lambda, let me call lambda 2, yeah. Lambda 3 equals to the 2/3 of the L. And then we have a 3 equals to the 3V over 2L, because it's V over L, and L is 2 over 3, so 3 goes up, 2 goes down. And this one is equals to the 3F1. We call it third harmonic. And now let's draw the pressure. Should I draw it in a... No, I would draw it on the same tube. So I would draw it by the red color. The pressure would be, we said, since we have the antinode here, and it's the air molecules can move freely, we have the minimum pressure. So here we have nodes for pressure, and here we have a node for pressure. So it would be something like this. Now let me try. It would be something like this. We have the antinode at this point when we have antinode pressure, when we have the zero displacement. And for the second one, again, same thing. We have nodes of pressure when we have antinode, and we have antinodes of pressure when we have node of displacement. So it would be something like this. And for the third one, again, same pattern. Antinode of displacement have a node of pressure. Node, 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 and then we have antinode over here. Then we create a pattern like this, and this is for the case 1 and open tube. And now let's go for the second one, open close. Now let's talk about the second case, the open closed tube. The open end is still displacement antinode, the max movement, but the closed end is a wall. So the air molecules cannot go through it, so they cannot move. The closed end must be a displacement node, zero movement. Let's draw them for the 3 possible modes that we have. This is our tube. Notice that it's closed at one end. The other one, let's draw another one. Another one, and here we go. So now I don't like this one, so I can just copy and paste it. Here we go. Okay, so now let's talk about the first mode that we have. The rule is, as we said, antinode at open end and node at the closed end. So we have antinode here, because the air molecules can move freely, and since this one is wall, so they cannot move, we have node here, the minimum displacement. And the pattern would be node, antinode, or antinode, node. How much of a wave? So now, what is the simplest, longest wavelength pattern that fits? It's just a single gentle curve from the maximum movement at the open end down to the zero at the closed end. And this is an antinode node pattern or node antinode pattern. Because how much of a wavelength is that? It's not half of a wave, it's exactly 1/4 of a full wavelength. So for the fundamental frequency, L equals to the, F1 100 hertz, L equals to lambda over 4. So now, let's try to talk about the first mode, our M1. We said we have an antinode here, and we have a node here, and our L is equal to the 1/4 of a lambda. So it would be something like this. This is how it would look like. And deriving that, we can conclude that our lambda 1 equals to 4L, and F1 equals to the V over lambda. And since lambda is 4L, it would be V over 4L. This is called our first harmonic. Let's just talk about the pressure here. We said when we have the node for displacement, we have an antinode for pressure, and when we have an antinode for displacement, we have a node for pressure. So here, now we have a node for displacement. So our pressure points is antinode. And here we have antinode for displacement, so it would be in node for pressure. So the pattern would be something like this. And this one, let's call this our pressure to not get confused. And this is our pressure. The white one is our displacement. I would write it up. Now, let's get to our second mode. What do you think would be the next possible frequency? It still needs an antinode at one end and a node at the other. The next shape that works is node, antinode here, antinode, then node, antinode, node. If you count the section, that's 3/4 of a wavelength inside the two. So our L equals to the 3 lambda over 4. And the frequency of this wave is 3 times the fundamental frequency. This is the third harmonic. But wait a minute, what happened to the second harmonic? If we try to draw it, a second harmonic would need an antinode at both ends or node at both ends. That's impossible for a pi that's open on one side and closed on the other one. You simply cannot form a standing wave at twice the fundamental frequency. And this pattern continues, and the next harmonic that works fits 5/4 of a wavelength, which has 5 times the fundamental frequency. And for an open closed pipe, a surprising new rule emerges. Only odd harmonics are present here. The followed frequency are 1, so we only can have 1, 3, 5, 7 times the fundamental frequency. This is a deep, non-obvious result that comes from the physics of the boundaries. Those missing even harmonics are a huge part of what gives instruments like clarinets their unique hollow or woody sound compared to the brighter sound of flutes or like violins, which have all the harmonics. And now let's get back to our shapes. What would it be? How will it be look like? So let's show nodes here. Oh my god. Node here to be evenly distributed. So we said this is our node, this is our antinode, and this is our node again. and this is our antinote. So the shape would be something like this. It's a bad one, but yeah. So now let's go for the pressure. When we have a note for displacement, antinote for displacement, we have a note for pressure. So our pressure would be something like this. Notice that in the antinote, from the node point for displacement, we have antinote for pressure. In the antinote points of displacement, we have note for pressure. And now, this is our M. I'm sorry, guys, I don't know why I wrote 2. This is our M3. We have third harmonic. And here, again, L3, lambda 3 equals to the 4/3 of the L. So our third harmonic would be 3V over 4L, which is basically 3 times the fundamental frequency, and it's called third harmonic. And if we go down, again for this one, node, antinote, node, antinote, node, antinote. And it would be something node, node, node. It would be something like this. And our pressure again, since we said the node for the antinode, for node for displacement gives us an antinode for the pressure, it would be something like this. Let me draw it. Something like, again here, like this, and like this, which is similar to this one, and that's for the second case, open, closed. We get to our third case, the closed tube. So, just to be complete, a tube closed at both ends would need a node at each end, and this association end up being musically identical to the string fix at both ends and open tube. All harmonics are present, and it's basically the same as the open one, but I'm just going to show like this first harmonic and the second harmonic. I'm not going to talk about the third harmonic. It's just similar to that. You know the pattern, you can draw it. So this is our tube. This is our closed tube. So M1, since there is a minimum movement, so we have a node here, and node, and again, node, and we have an antinode in the middle. So it would be something like this. And notice the difference. Instead of like, let me draw it here. Instead of being like this, it's now like this. But again, they're both are half a lambda. The L lambda is equal to L1, lambda 1. And our first harmonic frequency would be V over lambda 1, which is V over 2L. And it calls first harmonic. And our pressure, and our pressure would be similar to the open case. It would be like this. Yep. For the second mode, second harmonic, we have something like this. And for the pressure, it's like this. Notice that it's similar to this pattern here for the node, for the displacement. And again, lambda 2 equals to L frequency. Our second harmonic frequency would be V over L, which makes it 2 times the first harmonic, and this one is called second Okay, so now let's talk about other manifestation of standing waves. These incredible patterns aren't just for music, they're universal features of our world, showing up in some familiar and some truly mind-blowing ways. Mind-bending waves. So now let's talk about the microwaves. Have you ever cooked something in a microwave without just the rotating plate and found these spots are cold spots? Nice, you just found the standing waves. Microwaves work by filling a metal box like this. Metal box by filling a metal box with electromagnetic waves. These waves bounce off the wall and create giant 3D standing waves. So for example, this is our wave, it goes this way. And then there's another wave in phase with it. They would get a bigger wave here and with a much higher energy. The hottest spot are the antinodes, where waves energy cooks your food. The coldest part are the nodes, where there's almost no energy, no heating. The turntable is just a clever fix to move your food through all nodes and antinodes for even cooking. And now we can put laser also as an example, and microwave waves and laser are an example of standing electromagnetic waves. So if you have a laser cavity like this, and these are called this is called full reflector, and this is called partial reflector. It partially reflects some of the electromagnetic waves. Reflector. This is the overall thing called laser cavity, and if I want to draw the waves, I mean this one is too small for it, but yeah, something like this. Oh my god. Okay. Something like this would be our standing light. It just goes back and forth and creates enough energy, and then standing light wave. You would produce, draw it in red, you would produce laser beam. So in the next video, so now let's not finish it. Let's try to do some examples and then we can finish this video. Try to solve the next example, pause the video and then check your answer with mine. Pause the video and try to answer this question. It says an open tube of air supports the standing waves at frequency of 300 Hz and 400 Hz. And at no frequencies between these two. The second lowest standing wave supported by this tube has frequency of, and what if one end of the tube is closed now? So we said, for an open tube, all harmonics are present. So our Fn equals to the n times F1, where n is an integer of 1, for example, 2, 3, and so on. We given two frequencies of 300 Hz and 400 Hz, with no other allowed frequencies between, so they must be constructive harmonics. So we assume that, for example, Fn is 300 Hz, and if Fn plus 1, because it says there's no frequencies in between, Fn plus 1 is 400 Hz. So our Fn plus 1 minus Fn, n plus 1 minus Fn would be equal to F1, which is 100 Hertz. That's it. So the fundamental frequency, or F1, would be 100 hertz, but it wants the second lowest, so our second harmonic, which is 200 hertz, or 2 times f1, which is again 200 hertz. Now let's go for our second question. It says, what if one end of the tube is closed now? For an open closed tube, only odd harmonics are allowed. So our Fn equals to Nf1, where n equals to 1, 3, 5. And since the tube length does not change, the fundamental frequency becomes half of the open fundamental. And if you don't know how I drive that, go back and look at it. For the first for the open close fundamental frequency, we have V over 4L, and for the open we have V over 2L. And if we try to say, okay, V over 2L over V over 4L, we get the answer of 2. We get the answer of 2, and this one is our F1 over F2. So our so the fundamental frequency becomes half of the open fundamental. So F1 open closed equals to half of the open. And now we get half times 100 is equal to 50 hertz. So the open closed tube supports our F1 is 50 hertz. Our F2 would be 150 hertz. What? 150 hertz. You might say, why didn't you multiply it by 2? Because for open close, our integers are 1, 3, 5. 1, 3, 5. And F3, I'm sorry. Oh, this one is 3. I'm just like the second one, which is the third one. Sorry, guys. F3. And now, what do you think would be the F5, our third harmonic? Like, it's our fifth harmonic, but the third pattern that we have. It would be 5 times 50 hertz, which is 250 hertz would be our fifth harmonic. And now let's go over another example. In this example, I've tried to review the concepts that we go over on. So it says an open closed tube with air length L has a closed end on the right, which is a displacement graph of the n equals to 3 standing waves in this tube. So by now you should know that when we have an open end, it means that here we have an anti-node, because the displacement would be maximum, air molecules can move freely. The end, we have the node here, and the pattern would be node, anti-node, and again node. So the graph would be something like this. Notice the difference. Open closed here. We have something like this, but here it's more of an inverse of it. And the reason is simple. Our closed is on the left, but here our closed is on the right. And now let's get over another mathematical question. And yep, I tried to pause the video. So this question is basically combining the concept of speed and frequency. So is at room temperature, the fundamental frequency for an open tube is 500 hertz. If taken outside on a cold winter day, the fundamental frequency would be, so let's start by the fundamental frequency of an open tube is F equals to 2V, V over 2L, I'm sorry, V over 2L. And how can we calculate our V? V is approximately 331 plus 0.6 times T, in which T is in Celsius, and then we can consider that it's a cold winter outside, so it's 0 degrees, and the room temperature is 20 degrees. So let's consider those temperature. Our V would be, we have two different V's. V1 is 331 plus 0.6 times 20. This one, V2, is equal to 331 plus 0.6 times 0. And this one is 1. 0, I mean, if you give us, again, same. I thought it's a power for a second. And this one would give us 343 meters per second for at room, outside. So now, let's go to calculate it. Before that, let's talk about it. If our V goes down, the frequency goes down too. But if our V goes up, the frequency goes up too. So which one do you think would have a higher frequency? Right, the in room. So now we want to find the ratio of their speed. Using the ratio of speed, find the frequency of cold. F cold over F room equals, since it's just the same, their relation is just like V, we don't need L because L is same. So I mean, if we want to ideally calculate it, the L can be changed through different temperatures, but here we use an ideal length, so we say it's constant, and we call it this one V cold over V room. This one 331, 343, which gives us approximately 0.965. And so we can multiply this number by our frequency of room, which is 500, and we get the number of, it does have, okay, didn't show it, 482.5 hertz. So that's so if the tube taken outside on a cold day, the fundamental frequency would decrease to approximately 482.5 hertz. And that's it. If you like the video, please subscribe and like the video. If you have any further question, you can comment it. I would definitely answer it. Thank you for watching my video.